Okay, so this is what we went over yesterday. Talk about it again. Okay, our strategy for mathematical induction. We need to prove, well, first of all, we're going to get a statement. Okay, now our statement is going to look more like an equation. The sum of a series equals this expression. Okay, we're going to prove that it is true. Okay, so our steps, we need to show that P1 is true. We need to knock over that first domino. Okay, and then we need to show that if p sub k is true, then p sub k plus 1 is true. Okay, if we can show all that, then our statement that we started out with is true. Okay, so we have our train of dominoes that we're knocking down. If any domino knock over the next one, when you start with the first one, they're all okay. This is also something okay. This is something we looked at yesterday as well. Okay? We have to, I mean, this is basically summarized. Okay? Show the first one is true. Okay? Then we need to create our domino effect. Assume k is true until we can prove k plus 1 is true. Okay? So here is what we're going, here's like step by step what we need to do. Okay? So we have a statement. We have a formula, basically. We have an equation. First step, number 1. Verify the formula is true for n equals 1. So basically, you're going to take the first term. Okay, so let me show you. Like something like this. Something like this is what we are going to be proving. Okay? So basically, we're going to have a sum of a sequence equals an expression. So we're going to take the first term on the left, we're going to plug in 1 on the right, and we're going to verify that is true. Then, our second step, we are going to assume that the formula is true for n is k. So we're actually going to write assume, we're going to plug in k. Or we're going to replace n with k. Okay? Then we need to show that s of k plus 1 is true. So we're going to plug s of k plus 1 into the left side, and we're going to play around with it until it equals whatever piece of k plus 1 is over here. Okay? Once we get there, then we're going to write a conclusion. Okay? This is not just going to be a bunch of numbers. We will write a little bit. Okay, we need to write the word assume for the second step. Assume that blah, 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 blah is true. Okay. Then we're going to plug in k plus 1, and we're going to show that they're equal. And then we're going to write, okay, therefore, our formula is valid for our natural numbers. Okay, so this is going to lay out like a proof. Okay, we're going to have to write a few words here and there. Alright, this should, anybody who is not in this class should be able to read it and follow along with what's going on. Okay, they may not completely understand why you're doing what you're doing, but they should be able to read through it and understand the logic. Okay. Any questions before we begin? So what we're going to do, we're going to look at a couple examples, and then I want to give you time to work on this during class, especially since I'm not going to be here on Monday during the review. Okay. We're going to prove that this formula is true. Write it down. All right, so our proof. First step, what do we need to do? Okay, so, what's our first term in our series here? 1. Does that equal 1 squared? Okay, so that is verified. That's good. We're off to a good start. Okay, now, the first part of the second step is to do what? Assume the formula is true. So we're going to write the word assume. I want to see that. Now we need to work with k plus 1. Okay? Okay, so we're going to assume that this is true. Then if this is true, okay, what is s of k plus 1? Okay, this is where our practice yesterday is going to come into play. Our series for k plus 1 is 1 plus 3 plus 5 plus 7 plus what? 2 times k plus 1 minus 1, right? Yeah. Which is the same thing as what? Now, I do have a question. What is the term before 2k plus 1? What's our... What do you say, Malik? Okay, good. Does everyone know how Malik got that? Okay, because we are adding up the first k plus 1 terms. To add up the first k plus 1 terms, we're adding up the k terms, and then we're adding a k plus 1 term. So we still have these k terms right here, don't we? We will. Okay, that is good. Our goal, okay, is to show that this is going to equal what? Okay. What? What are we trying to prove it equals? I disagree. We are trying to prove that each bit equals k plus 1, the quantity squared. That is our end goal. If we can get to k plus 1, the quantity squared, our proof is going to be complete. Are you understanding why? Okay. So, since this is k squared, when I'm looking at the k plus 1 series, my goal is to get it to k plus 1 squared. Okay? So what I would do if I were you, I would write out this step, figure out what you need to get to, and write that at the bottom so you know that's where you need to go. Okay? Now, we need to make this look like this. Any ideas? Now, we assumed that this is true. I just underlined something in red. What does that look like? That looks like this right here, right? Which is k squared. What? The 2k plus 1, that came from me adding the k plus 1 term. This is the series of the first k plus 1 terms. So here's the first k term, and then I added the k plus 1 term. So 2 times k plus 1 minus 1. This? Okay. Since this is the sum of the first k plus 1 terms, I have to have the first k term, and then I add the k plus 1 term. So I know that the term before this is 2k minus 1, because this is the k term, this is the k plus 1 term. Okay. Do you see what I underlined right here? Do you agree that that's the same as this right here? Well, what does this equal? K squared. Okay, K. Yeah, you're always going to have those first k terms, and you're going to add the k plus 1 term to it. Because we have a series. We're adding up a sequence of k plus 1 terms.
Do you even have to add the 2k plus minus 1 on that one? That section is just
you need to have this 2k minus 1 written so that you can actually compare it to this right here up top. Okay? Now, we have k squared plus 2k plus 1. Okay? We reached our goal. Awesome. Okay? Now, when you get here, okay, you remember how you always had to kind of conclude your geometry proofs?
No.
You always had to make sure you got to your ending point, right? So I want you to wrap this up. Therefore, S of k is valid for all, what kind of numbers?
Natural, that's what I meant.
What numbers? Okay, what we're doing is we're proving the sum of a sequence equals a value. Okay? We're proving that 1 plus 3 plus 5 plus 7, which is the sum of 2n minus 1, the sequence, we're proving that that equals n squared. It's kind of like proving a shortcut instead of having to do the n over 2 times first term plus last term. Okay, we're proving an even better shortcut. Does that make sense? We're proving that the sum of a sequence equals an expression. Okay? Other questions? That's the sequence that we're adding up.
See how up at the top next to assume it says that plus q squared? Oh, okay, yeah.
All right, so soaking in a little bit. Yes. If S of 1 doesn't work, you're not going to continue. Because if it doesn't work for the first term, it doesn't work for all. You can write bus. Sure.
Bus and product.
Next. We are basically adding up the series, or adding up the sequence of 3 plus 2a. Right? So, our proof. So the first thing, S of 1. What's the first term in our sequence? 5. Does that equal, when I plug in 1, 1 times 1 plus 4? Okay, 5 equals 5. Good start. Okay. Now, write the word assume. That is an important word. We are going to assume that k is true. So 2 plus 7 plus 9 plus 3 plus 2k equals k times k plus 4. Guys, just the backwards 2. Alright. What? Okay. First of all, let's write out S of k plus 1. Let's just write out the sum of the first k plus 1 terms. Okay? The sum of the first k plus 1 terms, okay, we're going to have the sum of our first k term plus what is our k plus 1 term? Okay.
2k plus 4. Or 4 plus
Well,
2k.
let's do this. 3 plus 2 times k plus 1. Alright? When we distribute that 2, plus 2k, correct? Okay. Now, what is our goal? S of k adds up to k times k plus 4. So we want to get to what? K plus 1 times k plus 5. That is our goal. We get there, we have our proof complete. Okay? What did we do to get that? Okay, anywhere there's a k, we replace it with k plus 1 because we're proving the k plus 1 series to be true. Okay, so your proof's going to be about the same every time. All right? What? Factoring is going to be a big part of it. All right? But this is always going to be an important piece. What is that? Same thing as right there, right? So we can replace this with k times k plus 4 because we assume that sum to be true. So we have k times k plus 4 plus 5 plus 2k, right? We need to get this to k plus 1 times k plus 5. What must we do? Okay, we better distribute that k and combine like terms, right? So we have k squared plus 4k plus 5 plus 2k, which we can combine to k squared plus 6k plus 5. Now, let's make sure, does this factor to k plus 1 times k plus 5?
It does.
Good. Therefore, every time S of n is true for all natural numbers. And make sure you put natural numbers. Did I write S of k last time?
Yeah.
Okay, it should be S of n. I'll go back and fix that. It should be S of n because that's what they give us to begin with. Okay? And that n, what is that n standing for? Your natural numbers. N is standing for the natural numbers. Yes. Okay. If the sum of the first k terms is k times k plus 4, then the sum of the first k plus 1 term is going to have to be this, but we're going to replace each k with k plus 1. So k became k plus 1, k plus 4 became k plus 5. Okay. Other questions? You don't have to write very many words, but notice how we can read this, okay? The first term works. We're assuming this to be true. So now S of k equals this. We get to here. Therefore, okay, I'm wrapping up. When you write a paragraph or an essay, you have to have a conclusion. This is the conclusion to your essay, aka your proof. Okay, but most of your essay is in the proof. Well, it looks more like 3 paragraphs. Yep. Okay. Now, in your homework, on your review, on your test, I want your proofs to look like this. Okay? You cannot go from this step. Well, you can't go from here to here. You need to go in logical order. I need to see, okay, kind of like you did your geometry proof. You had to say something about parallel lines before you could say something about corresponding angles, before you could say something about congruent angles, okay? Make sure every step is logical and you don't skip anything. I'm going to act like I don't know how to do this when I grade it. Okay, so everything should make sense to me. This?
Why when you on the 3 plus 2k, why wouldn't you do 3 plus 2 k plus 1 in that like same bracket? Because it's like it's the same in the next. Oh, then you're just counting the 10.
Because what this is, this right here is starting 3. This is the sum of the first k plus 1 term. So I have to add up the first k terms and then add the k plus 1 terms, right? If I want the sum of the first 3 terms, then it's 5 plus 7 plus 9. The first 4 terms, 5 plus 7 plus 9 plus 11, right? So you have those 3 present and then you add the 4.
So you just keep the.
You keep the k terms and then you add your k plus 1. Okay? Now, you don't have very many problems, and you have a good 20 minutes to work on this. Okay? Please call me over if you want me to check any of your work. Because it's a proof. There are not answers in the back of the book. I do have my answers.
There's no answers in the back of the book. I'll tell you what Katie says. I'm walking to school, I don't text and drive. I'll say Miss Onions drive. Oh, wait.